Last time.
Okay. I will speak about jet ideals and products of ideals and differential rings, but I would postpone all formal definitions and formal results for the second part. And first part, I'll just show you some computation which will illustrate phenomena which I'm interested in. The most simple example is the following. We know that xy is equal to 0. Okay, just let's not focus on what are x and y. And we are interested if x prime times y equals 0. Okay, if we know that x and y, for example, are power series of meromorphic functions, the answer will be definitely yes, because if two functions, product of two functions is 0, okay, that's one of them is 0, then okay. Even if they are real functions, of course, it will also imply, but if we restrict ourselves just to some certain algebraic operations, which actually correspond to definition of differential ideal, if we allow ourselves do the following two things, multiply by any polynomial in x, y, and their derivatives, and just formally differentiate the expression. Can we deduce x prime y equals 0 from xy? Actually, it can be shown that we cannot do that. Okay, why? Just let us look at all formal derivatives of xy equals 0. They all are homogeneous of degree 2. And our target is also homogeneous of degree 2. So if there is a way to obtain it from these equations, then the only thing which we can multiply it by are scalars. Because if we multiply any of these equations, say by x, for example, it will be of degree 3, we can throw away this component. And also, now we need just to check that x prime y is not a linear combination of these equations. Okay, it also can be easily checked because from this point and on further, every monomial contains at least two derivatives. That's too much. So, and this one here, every monomial contains 0 derivatives. Too small. So the only way to express this equality is express it as linear combination of only one equation. It's impossible. So just some kind of linear algebra, this result. But if we allow ourselves to take square of x prime y, then we can express it in the way we want it. So this is derivative of xy, this is xy, and here are some just polynomials which multiply by.
So if you allow square roots, in other words.
Okay, if I allow squares or square roots, it's yeah. So
express.
Yes. So just again, small comment. Why are we interested in these strange results? Because as I said, in like world of functions, all these questions are nonsense. But when you work in some on some differential polynomials, normally you leave modulo some differential equations which form some differential ideal, and it is really can be the case that you don't want to compute its radical because it's very costly. So it's really a normal situation when you leave modulo some differential ideal and modulo or even modulo some ideal, and in this situation all these effects really can occur. Okay, so but this was something simple because the non-existence of the formula was proved by some linear algebra because we have very low degrees. And the existence was proved by just construction. Okay, both these proofs are not very generalizable. First of all, let me explain how could we get this kind of result by more general reasoning. Actually, we can prove that x prime y in some degree can be expressed in terms of xy and prime y plus xy prime due to Hilbert's Stellensatz.
By the way, so you mentioned that a part of your motivation was computation just purely in the context of differential algebra.
Yes.
Don't you have other kinds of motivation?
I will say about that later.
Okay.
Yes.
Some suspense.
Yes. Now I just show, okay, formulas. I like these formulas. Okay, how can we prove that x prime y in some degree lies in this ideal? Okay, actually, if we just think about all these derivatives as separate variables, we can just make change of variables, and we want to prove that polynomial z2, z3 vanishes at every root of this polynomial system, which obtained from our system just by some change of variables, removing all the primes, just not to confuse ourselves. Okay, because if this is true, that either z3 equals 0, and it's already equals 0, or z1 equals 0, then this equals 0, and z2, z3 equals 0. Yeah?
The way you are invoking Hilbert's Stellensatz sounds like you should be able to say that since if you take just one variable, the polynomial w vanishes at every solution of the polynomial w squared. So I should be able to write w as a linear...
W in some degree.
In some degree.
I have a quantifier on D.
Okay.
Yeah, sure. I don't check membership by this reasoning, of course. It would be great, but not in this galaxy.
And presumably, using effective Stellensatz, effective polynomial Stellensatz, we can get an upper bound on D, right?
Yeah, sure. Of course, I can get an upper bound for this D, and okay, in this case, it will be quite modest, but I think not 2. Because we have two polynomials of degrees 2, so I think it will be something like 4.
Okay,
so
that's reasonable. Some bound, I'm guessing.
Yeah, okay, but after all, we have some theoretical way to prove that this degree exists without just showing explicitly. Okay, and the second example actually is...
But you can also, so since you have a bound the polynomial Stellensatz, polynomial effective Stellensatz, you can get an algorithm because you raise it.
Yes, sure. Yes, I of course I have an algorithm in this way because yes, I can just raise to big enough power and check by any.
So you can ask the computer to prove your theorem.
Yes, but it stacks quite. Okay, for quite small numbers. I asked him. Okay, and this is a real example in the sense that in order to deal with this example, we actually need to use almost all methods which we need to prove any general theorem about this kind of phenomena. So let me say in what kind of phenomena I'm interested right now. I have yes, I know that xy equals 0. I allow myself to differentiate it several times, like to get x prime y plus x y prime, and so on. And I want to understand if all this implies something like eighth derivative of x equals 0. Again, in some degree. It's reasonable to expect something like that because, again, in the world of functions, which will happen for sure. But now, actually, we can ask about two numbers. One number is how many equations, how many times should we differentiate? and how large the degree will be. So, in this specific example, I have x2 prime y prime, and I took 3 derivatives, and I claim that this is actually sufficient. Of course, again, I can use reasoning by Hilbert's Neustadt-Satz, but now I have much more. I have 4 equations, and I have 8 variables. So, okay, it's not that easy to think about that, and I want to propose some more compact way to write down all these defined equations. Actually, we can encode all these 4 polynomials into one in the way this is suggested below. Let's write this expression. Let's write it for small number. Let's consider something which looks very similar to Taylor series. So x plus x prime t plus, and the same for y. And let's just expand the brackets. The constant term will be xy. Linear term will be x prime y, xy prime. And you can check that quadratic term will be this. Which is actually second derivative. And there will be something of higher degree in t. Okay, again, it's actually some algebraic analog of all the Taylor formula things. And actually this is how all these things are connected to jet spaces and jet ideals for algebraic varieties. But for now, for us, this is a compact way to think about all these equations as just one. And now we can try to prove that the fact that this product vanishes up to order t to the 4th implies that x2 prime y prime vanishes. So and one more term here. And write the same thing with y. And what we know now, we know that first 3 derivatives of xy are 0. So this thing, if we expand brackets, will vanish up to order t to the 4th. So now, okay, let us take any solution of this system as system of algebraic equations. So let us think that all this x prime, y prime, and all these variables are some numbers. Okay, some of them are non-zero. But if you take this part and this part, and there is at least one non-zero number here, and at least one non-zero number here, say this is the first non-zero, and let's say this is the first non-zero. Then we'll see that linear part of the product will be also non-zero. So all these things are zero, all these things are zero. So in particular, either all these things or all these things are zero. So either x2 prime is zero, either y prime is zero. And this kind of reasoning works actually for arbitrary number of derivations of x and y. You'll just take longer parts of this series. So that's how we can prove that in some degree this differential polynomial is a consequence of that system. Again, as in our first example, we can't prove that this degree is not 1. This is some linear algebra. But actually it is 5, so it's a question how to prove that, for example, it's not 4. It's much less trivial thing. Okay, this is what I already said.
And why would you want to prove that it's not something?
Now I will describe some strategy on how to prove that something is not zero.
Why would you want to prove that it's not something? If you find some number that's good enough for you, why would you want to do it?
I'm interested in minimal number.
So you explain why you want a minimal number, right?
Yeah, okay. Then I have some number. I'm curious if this number can be improved.
Why?
Yeah.
Will you explain or not? Or maybe it's later, after the talk.
Later.
Later.
I'll explain later. So, how can we prove that something is non-zero? Okay, from purely algebraic standpoint, we live in a ring of polynomials in that 8 variables, and we have our ideal. Just denote things which we already have. And for example, we want to prove that this polynomial doesn't lie in the ideal. How can we do that? We can construct a homomorphism from our ring to somewhere where we can compute easily, for example, to the field. And if we will see that kernel of this homomorphism contains our ideal, but the image is non-zero, then we have a proof. So in this situation, we can construct homomorphism just to the field. We just say that all derivatives of order less than 3 are zeros, and derivatives of the third order are ones. Then all derivatives of xy up to order 3 will be 0, because there are sums of products, and in each product at least one derivative is not for the 3. So ideal lies in the kernel of homomorphism, but the image is not 0. In fact, this proof is actually like converse for Hilbert's Nullstellensatz, because it proves that I can replace 42 with any other number. So this is kind of simple homomorphism. For our main example, which is x2 primes y prime, we cannot expect to get a homomorphism field, because we just checked that for every solution of this polynomial system in a field, it will vanish. So if we need to come up with something more subtle, and here it is. Okay, this might look strange. Let me just explain how can we come up with such formula. What do we want? We want to substitute something instead of all x's and y's and get all to t to the 4. Okay, we start with some. Okay, it's reasonable, but it looks arbitrary choice. We just say that. Okay, let's just say that all third derivatives are zeros and all second are ones. So that's what's written. This is what was written here. I just want to lower the degree. So erase this part, erase this part, and replace this thing by 1, this thing by 1.
So how do you decide how many you want to fix?
That's a good question. I want to have sum of degrees of the resulting two polynomials be equal to this 4. So the reason why I deleted third and third power is that 2 plus 2 is 4. And now I know that if I expand on brackets, I will have something of degree 4, and I want it to vanish up to degree 4. Okay, let us just pretend, okay, these are two quadratic polynomials, so we can imagine that they have roots. Let's imagine. Assume that these two have roots, so this polynomial will become x plus z1 by x plus, t. The polynomials in t, these polynomials in t, they have some roots. Just imagine, let's call them minus z2 and minus z1. Then what I wanted this thing to be, I want this thing to be equal zero up to degree 4. So due to the theorem, it's exactly the same to say that all symmetric polynomials, elementary symmetric polynomials in Z's vanish. So thinking just about that imagine situation, let's say that we construct homomorphism by these formulas. Again, these formulas are just Vieta's formulas for quadratic equation. And we construct homomorphism to ring of polynomials in Z's modulo all elementary symmetric polynomials. And now what happens next is, okay, kind of good luck, because okay, this is the same what I said. If we replace, these two polynomials can be factored, and then we can just use that all elementary symmetric polynomials in Z's vanish. And it turns that this polynomial, this homomorphism, its kernel is almost equal to our ideal I. So I don't want to make precise statements, but it captures this ideal very well. And the second good thing is that for ideal generated by elementary symmetric polynomials, there is a very well-known Grobner basis for arbitrary number of variables, actually. And Grobner basis is a good thing if you want to compute something. So this is the well-known lemma. How does this Grobner basis look like? Actually, this can be generalized to arbitrary number of Z's. So I just take sum of all variables. Then I take sum of all square monomials of all variables except the first. Then I take sum of all cubic monomials of all variables except two first. And then I take sum of all monomials degree 4 of all variables except first 3. So the pattern, again, is more or less understandable. Yeah, this is Grobner basis with respect to lexicographical ordering. This is some well-known fact. So now, if we want to prove that something is non-zero, we can just use this homomorphism, reduce with respect to this Grobner basis, and look, if it's non-zero, then we are lucky. But okay, for this concrete example, this can be done by hand. You have polynomial, you have Grobner basis, you just reduce by hand or by computer. But if you want to have some general statement for some arbitrary n, it's a bit harder, and this is another very unexpected fact. The fact is that, let me just take 2 steps back. This ring, when you take polynomials and factor out all elementary symmetric polynomials, which this ring turns out to be very well studied by geometry people. The reason is that it's a cohomology ring of flag manifold, whatever it means. And when you have cohomology ring, you really want to multiply things, because this corresponds to intersection. So these geometry people have a very good theory called Schubert calculus, which has nothing to do with Grobner basis. It's completely another thing, but it allows you to compute modulo all symmetric polynomials very good in some situations, and you agree with their notation. And it turns out that it's exactly what they need in this situation. For example, using the Schubert calculus, you can prove the following fact, which can be understood by undergraduate student, that if you take 2 variables and raise them to this power, this is modulo this ideal equal to this monomial where C is Catalan number. That's what I obtained by computation. I don't have any good proof of this. This is fact, looks elementary. You have polynomial, you have ideal, and you claim that this polynomial of Catalan numbers modulo this ideal is 0. So it's a very elementary thing, but I don't have short enough elementary proof. The only short proof I have is using Schubert calculus. That's funny, I think. So in such a way you can prove that something is non-zero, and you can prove that something is 0. Again, using the Grobner basis, because this Grobner basis actually bounds degrees of all variables. Let's just look at it back. This Grobner basis says that if you have reduced form, polynomial cannot contain z1, can contain z2 in degree at most 1, can contain z3 and degree at most 2, and so on. So it gives you some upper bound on what you can expect, and this upper bound can be defined by the fact that there's also a surprising fact that this Grobner basis respects symmetry, because it's not symmetric with respect to all variables. But if you take any polynomial with some symmetry, for example, with respect to 2 variables, zi and zi plus 1, and reduce, it will remain symmetric. Again, it's some fact which looks for me elementary, but I have only very long proof of it.
Well, why does it surprise you?
Because the generators of Grobner basis are not symmetric. So, for example, if you exchange z1 and z2, you will get another thing. But if you have something which is symmetric with respect to z1 and z2, and you reduce with respect to these polynomials, you will get again things symmetric in z1 and z2. If you have any high-level explanation of this phenomena, I will be very grateful. But I can prove it only for this specific Grobner basis. And this is some, not very elegant proof.
If you permute variables just that occur in each polynomial. So polynomials don't change.
If you permute any variables, this set of polynomials
will... Well, within those that occur in each polynomial.
There are no 2 variables which occur in each polynomial.
No, for each polynomial, look at the variables that occur there and do the permutations.
So like the second polynomial, just permute 2, 3, and 4, you'll get the same polynomial.
Yes, of course, but
so it's not completely independent. It's
it could be so, but no. I mean, if you, for example, just erase tails in every polynomial, it won't be so, because, for example, if you just consider Grobner basis of z1, z2 squared, z3 cubed, and z4, it also has a lot of symmetries. It will not preserve symmetry. So maybe there is some deep reason That's something good. Yeah.
Well, I mean, the system here is triangular in some sense, right?
Yeah, it's triangular.
So that's why it's not symmetric.
Yeah, sure, but it preserves symmetry. That's
Well,
what's
I
strange.
think what you multiply to those guys,
Mm-hmm.
basically you multiply.
Mm-hmm.
You subtract from the original polynomial, that's the result, right? Maybe what is multiplying basically make the product symmetry. This one times, this guy's times what you multiply. Together make this symmetric elements.
Yeah, because the original polynomial you're starting with is symmetric.
Yeah.
That forces the coefficient in the equilibrium basis to. I think that's what you're saying.
That's right.
So you say that if we have symmetric polynomial and its reduction, then what happens? Sorry, don't get
When you reduce it,
Yes.
you're subtracting a multiple of this.
Yes.
But the multiple itself has to have symmetries because the original polynomial is symmetric. So if you swap variables in the original polynomial,
You see,
it's not proof, it's just sort of a.
it's a good reason, but I mean, not every polynomial which you want to reduce with is symmetric with respect to the same variables.
Okay, that's possible.
So it's not rocket science. You can prove this fact by hands. You don't need to calculus, but it's not very easy. Okay, so now I have finished with examples. Now I want to explain what is differential algebra behind that and what problems in differential algebra did we solve in that way. Okay, let me
And
just
problems outside of differential algebra.
and problems outside differential algebra. I will say about them. Okay. What we worked during last 40 minutes were differential polynomials. I hope you also got used to them. This is just from abstract point of view, is an algebra and infinitely many variables where we define derivation just by increasing the upper index. So it represents, it's the usual thing to represent algebraic differential equations. Okay, now if you have an arbitrary differential algebra, then during the computation you usually work with some finitely generated ideals in this algebra, because we cannot handle infinitely generated things easily. Maybe we can. So if you have just some ideal and you want to speak about all the differential consequences, normally you can speak about all its differential consequences up to some order h. So you can prolong it h times, so add to the ideal all its generators differentiated up to h times. And what was the initial question is how this prolongation agrees with set theoretical operations like product and intersection. So what will happen if we'll multiply to prolong ideals or we prolong a product, and what will happen if we intersect to prolong ideals or if we prolong their intersection.
But there is something deeper behind this motivation, so this is used in other.
Okay. This problem actually occurred while studying effective differential Nullstellensatz, because when we studied differential Nullstellensatz, effective differential Nullstellensatz, we wanted to reduce our problem for an arbitrary ideal to problem for a prime ideal, for example.
So that we can use triangles.
Yes. So we can use triangle sets on some other good facts about prime ideals, actually. Then, if we have some just radical ideal, it's intersection of prime ideals. We can work with prime ideals separately, and then go back and use our result to reason something about the initial ideal. So, for example, if you find some polynomial in all these prolongations, then we can say that its degree lies in this prolongation. So, if you want to solve some membership problem for ideal I, we can try to solve it to its prime components, and then put things together using this inclusion. So actually, these two equations are closely related because the product of ideals lies inside the intersection. So we can reduce one to another and think only about products of ideals, because product is like more algebraic operation. And in our paper on effective differential Nullstellensatz, we proved that if you want to prove any fact of this form, to prove the corresponding thing for differential indeterminates. Okay, it's reasonable because you replace every ideal by some is generic element. Okay, it's reasoning behind this lemma. It's not that obvious, but okay, the reason is that just instead of thinking about the whole ideal, you say, okay, let's pick any generic element from this ideal. If we prove this for generic elements, then we prove it for the whole ideal.
Could you explain to me about what H is without subscript?
H without subscript.
What is that?
With subscript or without?
Without subscript. What is that?
Where is? It's some natural numbers. So it's
No, but H without the subscript. So what is the index for? You find it.
X
It's
moment
exactly.
on the first inclusion.
So it's equal to the sum.
It's a sum of the
H.
H's asymmetric.
Sorry. This is sum of H's.
Okay, thank you.
Yes, I'm sorry, I forgot to put this here. Yeah, thank you very much. Yes.
But this sort of sounds like it's saying D and H are, it doesn't matter what they are. It's just saying the first inclusion holds if and only if the second inclusion holds for any D and H. Right?
Yes. So if we prove the second for some D and H,
right,
then we prove the first for the same D and H.
right. So
you're missing some quantifiers there.
Yes.
For all D and for all H,
yeah,
that's
exactly.
equivalent.
Okay, but it's the same that if for fixed, it's also
But,
equivalent.
but you're missing quantifiers for D and H. Yes.
Okay, sorry.
But you mean that H is equal to, that it holds for H equal to the sum of the H?
Yes. H without subscript is equal to sum of H's. And actually, this H can be lower. So if you take it lower by 1, you will not have this inclusion in general. So in this sense, if you fixed H1, H2, Hn, this H is minimal time you need to prolong. You can.
I mean, the sum is the minimal.
Yes, sum is the minimal time that you need to prolong to.
Or in other words, is that you can reduce differential algebra to algebraic.
Yes, some algebraic manipulations because this is actually purely algebraic equation.
That's right.
Yes, because it looks like inclusion in big differential algebra, but if you look in this inclusion, we don't need to consider any derivative of order higher than h, because it doesn't occur here, and it's just like a new variable. So now we live in some differential, in some finitely generated polynomial ring, which is generated by all derivatives up to order h. Okay, and here is our way of packing generators to one, and actually it is another theory which these results are connected to, because when you study some algebraic equation, like let me pick any system of polynomial equations, example. you can go other way. You can say that, okay, let's just now replace x and y with x0 plus x1t and expand the brackets modulo t squared, saying that t squared is 0. Then constant term will be the initial equation, just with zeros in upper subscript. But the linear term will have the following form. It will be x1 times this differentiated with respect to x. So if you just expand this bracket, linear term will be x1 times 2x0, which is actually 0.
I was certainly puzzled by why you go to this reasoning when you can just take derivative of the expression there.
Why is this derivative?
I mean, what I'm saying is that there's nothing but just derivative of the x squared minus y cubed.
Yes, yes.
So then why do you have to go through all this process of explaining details? Is there a reason? Is motivation for that?
Yes, yes. I want to show that if you expand the brackets, you'll get defining equations of tangent space at the point.
That's clear from the fact that you can just call x squared minus y cubed. There's another function called z.
Mm-hmm.
You have to simply do Taylor expansion. So
Yes, yes. It's equivalent to take Taylor expansion up to some order, or just replace and say that t squared is 0. It's more algebraic get used to.
okay, fine.
So, and here you'll finally get this is the derivative of this thing with respect to y. So the second, the same operation applied with order with degree 2 to arbitrary polynomial system will give you defining equations of tangent bundle of the variety. And then you go further, you will get so-called jet spaces of the variety. They are used to somehow characterize the singularities because, okay, what's singularity? Roughly speaking, singularity is a place where tangent space behaves not well. And if you consider these higher order tangent spaces, you'll obtain some refined information about the singularity. And in fact, what we do here, we study the singularity that you have just cross of two components, intersection of two components. So our calculations of differential polynomials also give us results on jet spaces for this kind of singularities. And actually this is geometric language which can be used to simplify some reasoning here. Mm-hmm.
In the previous theorem,
Yeah.
how hard is it to prove it?
What do you mean previous theorem?
Yeah.
This lemma?
This lemma, right.
Okay, it is not very straightforward because the main problem is that when I say that x1 h1's derivative of x1 is generic element of this ideal, it was not totally true because generic element of this ideal is like sum of derivatives of orders from 0 to h1. So you need somehow to explain that h1 is actually the worst case. And this is some work. You need So it's not very hard theorem, but it's not.
But these ideal I1 and IN and all that is not just generated by one single element, right? It could be any number of generators. Is that correct?
Yes, but
They don't have to be monomials either.
Sure, but you see, then you look at this ideal.
Yes.
This is generated by the following things. You pick one element from each ideal, multiply them, and if any of them lies here, then their linear combination lies here. So that's why I look only at monomials. Because if I prove this for monomials, I'll prove it for everything else.
What about relations inside I1 of the generators?
Okay, in general, for some good i's, this d can be of course lower. But if I want to prove something for any differential ideal,
What I don't understand is how does x1 can represent generically the whole ideal when it's generated by several polynomials, and where there might be relations among the generators?
Yes, but then you look at every generator of this ideal. This is product of just one generator from every ideal.
The relations don't matter.
The relations, the other generators don't matter for this specific monomial.
So, can I ask you a couple of questions? One thing is, what is the quantifier on D here? Are you saying that
For all d and for all h's, it's equivalent to prove this or to prove this for every differential ideal.
so for each particular D, the two conditions are equivalent?
Yeah.
D and for is everywhere.
So suppose I give you a D and you're given the H, and I actually give you an expression to show how this, the lower left corner here, is actually in the ideal, right, up to order H. I'll give you an expression, actual expression, to satisfy the lower condition. How are you going to use that to show the upper condition?
In other words, you ask me how to prove this lemma.
Well, that was the first.
Okay,
I want to know what the technique is, not exactly the details. But let's say, what technique do you use? So I give you a formal. I actually give you a concrete example that satisfies the lower one. How do you actually show that the upper one is correct, no matter what the ideals are?
Okay, I think it will. What you ask is some, let's say, technical things. I don't have high-level explanation. Let's speak about after the talk.
Is your proof constructive, for example?
It depends on what you mean on constructive, but yes.
Constructive means that if I give you now, so suppose I give you one single expression satisfying the lower one, right? Now I give you an arbitrary element of I1, an arbitrary element of IN, right? And the D, how do you show that expression is actually on the other side?
In this sense, it is constructive. So you can produce the way to show that all these things lie there. Yes, it is constructive. So if you are given the way to
whatever elimination you can do, all right, to produce the lower equations, you can apply that to the upper equation.
Yes.
A specific case of the upper equation.
Okay, but by the way, so maybe the quantifier still need to be.
It's all because it's all because it's a product. Yes, it is all because
for example, if you take some degenerate cases of the ideals.
No, let's just try to say that what quantifiers are.
So it's not for all D and for all.
No. What I think should be correct is for all D and for all H.
Yes.
The following two statements are equivalent.
Okay.
One statement is that this thing holds.
Okay.
Yeah.
The second statement is for every ideals in every differential algebra this holds.
Okay, so for all.
That's right.
So,
Yeah,
so
well,
let me
this
just
is
make sure I understand. Your x's down below are formal variables,
Mhm.
and they have no connection whatsoever with
The
the i's
variables
up
are
No.
That's right.
No connection.
Okay.
They're like generic representatives of any differential element.
So you could have a case where you have specific ideals I1 to IN,
Right.
where the top inclusion holds for a specific D and H,
Yes, but
even though the bottom doesn't hold, and the reason is that the top inclusion doesn't hold for every
yes.
ideal
Yes.
I. Okay.
Yeah, so I have two statements, one about differential polynomials and one with quantifiers for all ideals in all differential algebras.
So the one on the top, the D and H, can be lower than the one at the bottom? Is that
No,
right?
no, no.
For some specific ideals, yes.
Right, okay. So I guess the point is that the bottom is the worst case scenario over
Yes,
all
true,
algebras.
true. That's
Right.
that's actually the reason why this is true.
Mhm.
So then the answer to William's question is just that if you have the inclusion on the bottom,
Mm-hmm.
then whatever witnesses it in that polynomial ring, then
Mhm.
witnesses it in every algebra. There is no computation, there is no
Mhm.
exact
Yeah, I do.
construction, it's just the exact same relation.
Not.
And closed under some H.
I think the reason why it is true is because you cannot really have elimination in the usual sense because you're taking a product. And that restricts the way, so if you have an expression down below, and then you substitute for the xi's,
Mm-hmm.
arbitrary elements in any polynomial ring, in fact,
Mm-hmm.
then the same thing would be true because you can just make a substitution because it's a homomorphism.
Yes,
That's
yes.
why.
The
Because
things.
it's a product, so it respects homomorphisms. And that's the proof, in fact.
You're.
I mean, you're stating it in a very, very general sense for ideals. But actually, the upper statement simply says that for any n polynomials in any polynomial ring, doesn't matter whether it's differential or not, but of course you differentiate it. All right. The formula that you have from below that witnesses that inclusion can be used just by homomorphism for the upper one with a single element, not the ideal. But since I can do it for any element in any of these ideals, so that's true. Is that correct?
This is almost correct. The subtle thing is that if you want, for example, to prove that A times lie in anything, of course, you need to. It is sufficient. Speak about this. So you need to say that for every A I and for every B and G, this was bad idea. Yeah. Of course, you need to prove this. Yes?
Well, I'm only saying that the proof from the lower to the upper. All right?
Yeah,
I
but
don't know about
yes,
the-
yes,
I haven't
but-
thought about the other one.
But it is not the
But-
substitution.
but- Why not? So I take a substitute homomorphism
Mhm.
from the polynomial x to the polynomial in whatever other variable you want to have,
Mhm.
and the substitution is the xi goes to the fi that is in I of I, f1 in I1 and fn in In, and anyone. So that's a homomorphism that I could well define, right? Substitute homomorphism. So whatever relation you can write down below get mapped into the relation up above, right?
Yes, but what you just proved, you proved this fact if we define this prolonged ideal as an ideal generated by derivatives of order h1. But we also need to remember that there are derivatives of order less than h1. So what you really need to prove?
No, it's nothing to do with it. My expression down below has differential variables x1 up to xn to a certain order. Right? That's a relation.
No, have expression of exactly order h1.
Yeah.
Exactly order h1,
Exactly.
not lower.
Yeah, so when I substitute x1 into f1, then x1 to the whatever order derivative you needed, h1, for example, would go to f1, h1. It's a differential homomorphism. The substitution is a differential homomorphism.
So I think what Gleb is saying is that the notation is a little deceptive in that the x1 superscript parentheses h1 is not the same as the ideal generated by x1 superscript parentheses
No,
h1.
it's not, but it doesn't
Yes.
matter.
Okay, if you
question.
Okay.
What is that?
All right.
Could you say once
Okay,
more?
I got it.
What is the x1 to this?
No.
H1, what is it again?
Alice is correct. So the substitute homomorphism. So
So write down the definition.
Yeah. Let me answer the question.
So I1 to the h1
Mhm.
doesn't mean that it comes from the h1 derivative of a single differential polynomial.
Yes, that's what I
That's the
was
problem.
trying to
That's the
say.
problem.
Sorry, maybe I
That's the problem.
said it in
Okay.
backwards. Yes, answering the question of Kuhn, the subtlety is the following. I can consider this single polynomial, or I can say that I take a an ideal generated by x1 and prolong it h1 times, which means that I generate ideal by all derivatives of x1 of order from 0 to h1. So this is x1 prime, x1.
There upstairs is only order h1.
Yes.
That's
And that's actually not real thing in going from here to here. You need to somehow imply the lower order derivations. Okay, thank you. I'm sorry, maybe it might be misleading.
But still, when you say x1 sub h1, you also after you're forming an ideal.
Yes. So
So x1 is
yeah,
also
this is
an ideal.
polynomial ideal generated by this.
So upstairs, the top one.
Top one.
That's also an ideal.
This is a single polynomial.
This is a single
Top and
polynomial.
bottom
right?
are
That's a
different on the
single
board and
polynomial.
on the slides, so you're miscommunicating. So just erase your x1 in parentheses, the top line, and put it one line below. And then top and bottom will again be things.
Okay, I didn't understand what
It's consistent with.
Why is that in the parentheses?
Ah, okay.
x1, maybe you should just say I sub 1 is what you mean.
Well, let's go on.
No, we
We
try to
now understand what the distinction
We
is.
have spent sufficient
Okay, all right, fine.
time on this.
Thank you.
Yeah, okay, we can discuss it afterwards. I can give you all details, what you can imagine. Okay, so as I was explaining, this is essentially the investigating of the structure of this ideal is the same as investigating of the structure of jet space of the point of intersection of n hyperplanes of general position. So this is geometric counterpart of this fact, and in fact, for these jet spaces, some things were computed by algebraic geometers like multiplicities or prime components, and so on. So, let's mute. And finally, the result is the following. So this is what finally happens. So we can write down these expressions, and they are minimal. So if
In the sense that there exist ideals.
yeah, so there exist ideals where this inclusion doesn't hold. So and if
If you lower one of them.
if you recall our example, we had x2 primes y prime, so h1 equals 2, h2 equals 1. Then we'll have